Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell. You'll get notifications for this series and a bunch of other ones on our channel. We're doing multivariable calculus. This is chapter 2. We're on the tail end of chapter 2, and then we'll be into the good stuff, chapter 3, which is vector calculus, Green's theorem, Stokes' theorem, divergence theorem, those kind of things, the good stuff. What we're going to do today in this lecture specifically is we're going to do change of variable for double and triple integrals. You've already sort of seen this. It's called substitution rule for change of variables in one dimension. Let's do it. Change of variables, what's the idea? We've already done this in one dimension or one variable calculus. What we call it is a substitution usually. But especially in particular when we're doing definite integrals and we have bounds, we have to take care of what's actually happening. And we didn't point it out in the first year calculus because there was so much already and you were like, I hate this enough as it is. But so we didn't want to point out that we're actually doing general change of variables and Jacobians and those types of things for how areas and volumes and stuff transform and length when we transform these types of things in integration. So what that means in substitution is if you go from A to B and you have that x is actually a function of another variable u, say, then you're going to change your bounds if you recall. So I'm going to let a equal g of alpha and b equal g of beta. And then we can transform, and what we're doing essentially is using differentials this time, but we're going to get dx is equal to g prime u du. And this is where this is going to go into here. And so we had this formula and they proved this. We're going to sort of rephrase what that means now and write it in particular in Leibniz notation. Now that I see this, I have the derivative of g with respect to u times the differential du. And what we're going to get is the generalization of this notion for double and triple integrals. We've already done this in polar coordinates, and we got instead of in the single variable one, we got a dg du. In the double integral, when we switched from dx dy, we got a r dr d theta. So this is what we're trying to talk about in general. Who is he and where is it coming from when we do this general transformation? They're called Jacobians, and they're going to help us deal with general change of variables for double and triple integrals. For double integral change of variables, what we're going to do is first point out we've already done this and try and mimic the general idea of what we did with polar. There is something going on here, and it's just you don't just get dA or f of x dy dx doesn't just go to dr d theta, we get r dr d theta. So now we're going to explain why that's happening, where s of course also is, we have to be careful for general ones. S is the region in the r theta plane described for the bounds that we described in terms of the polar coordinates corresponding to the region r in the general Cartesian coordinates that we started with. So what we want to do is we want to mimic this idea for, instead of just writing x and y as r cos theta, what we've done is really written x as a function of two variables and y as a function of two variables. In general, and mimicking most of the calculus books, in general they're going to call it u and v at first instead of r and theta, but it doesn't matter. This is just, and then w, those are for three triple integrals. Those are just dummy variables for replacing, saying any kind of transformation x, y, z, functions of u, v, w in three, or if you're in two dimensions, it's this. Let's start doing the general idea of double integral change of variables. All right, the more general scenario is going to be we want to consider a change of coordinates from a uv plane to an xy plane. In general, you'll see that most of the time we're going to start with the xy plane and go into r theta, or when we have xyz, we're going to go into rho phi theta. The spherical and cylindrical ones we just talked about, those are also going to be the most general ones we use, but they want to talk about at least once that you can do this for any transformation. If I have to describe this change of coordinates, what we're going to actually do is use a bunch of linear algebra temporarily to get a clever formula for how you do the double integrals. That's what we're going to do here. If I describe that change of coordinates with a transformation from the uv plane, which you can't tell in that avatar, but they're different, and then this is the xy plane is what we're saying. And then we're going to have t of uv. I'm so used to writing them in linear algebra as vectors. So if you take t of uv, who is the vector now, and I'm going to say his image is these two coordinates, essentially in linear algebra, if these two functions were actually linear, we would call this a linear transformation and start talking about those two types of things, and we would do linear algebra. Instead, what we're trying to do here is just view a change of coordinates as a transformation, which is probably in most cases not linear. The things I want to recall from linear algebra that we're just going to quickly use and talk about for change of basis or change of coordinates is the fact that we say that if no 2 points have the same image, i.e. if u1, v1 is not equal to u2, v2, then their images are not equal to each other either. That says we call the transformation 1-to-1. And we want this process to be reversible. If we can transform from here to here, we want to be able to talk about going from backwards is all they're worrying about right here. So if you have a 1-to-1 linear transformation on a finite dimensional vector space, which these are, I don't have to talk about onto, and if it's 1-to-1, it has an inverse transformation t-1, which is going from the xy plane now to the uv plane in reverse. Why do I want that? Basically, I want to phrase our double integral formula through this determinant guy called the Jacobian, and we have to make sure our transformation is 1-to-1 and onto, and therefore has an inverse transformation. Let's do that. All right, the idea of change of variables, we're going to give this so it doesn't look like black magic, or you're just going to memorize where the Jacobian comes from and how to compute the Jacobian. But at least once, what's a Jacobian? Exactly. What we're trying to do here is we're trying to transform with the transformation t from the uv plane to the xy plane. Or when we do this, it'll be xy to polar or whatever we're doing. When we try to do this, what we want to say is, how does the area of this transform to the area of the new region that we're going to get? See, when we do this, when we do general transformations, that square might turn into a different shape in the image space. And what we want to know is, what are the areas corresponding? Are they the same? They're not identically the same. And they are factored by this thing that we're going to call a Jacobian, or the r dr d theta. It's not just dx dy equals dr d theta, it's r dr d theta. There's a factor in there, and we're trying to get at the factor. So we're saying in the original image or pre-image space, we have the area is delta A equals delta U delta V. But now when we go over here, what we're trying to say is, what's the area over here of the orange region? R. What we're going to do is we're going to set this up as vector calculus, and we're going to have this function r of u x y. Basically, it's actually this one. It describes it everywhere, but there's going to be one in this direction, and this one's going to be r of u, and then I'm going to hold v naught constant. And then in this direction, for this guy, I'm going to have r of u naught v. Technically, we're holding them constant, just like in partial derivatives or tangent planes when we're deriving these things. Therefore, I have this vector in the direction, and in particular on the boundary point, and then we pick a point and then one of the corners, or it has to be on the boundary of the region R, technical details. But once we have that, pick a corner for convenience, and it's on the boundary of that region R, then we have this vector. We can describe that as a vector function. Then what we do is at a point, we can now find the tangent plane to that guy. So we do. We're technically reviewing this in 3-space, cheating a little bit because I have to use a cross product soon, and that only works in 3 dimensions. So we're also viewing this as being in ambient 3-space, even we're talking about double integrals. Therefore, in the direction, in that tangent plane, we're going to have coordinates, and then we're going to have to try and mimic the idea of describing the tangent plane, approximating the tangent plane's area of that parallelogram as the approximate area of R, and then flushing that out with limits and giving us a change of variable formula for double integrals is the idea. Basically what we're asking is, if this is our R function, then we're going to get the rates of change in the U direction and the V direction are going to be these guys. And then what we're going to see is we're going to try and approximate the area of the actual region with the tangent plane parallelograms. Let's find a formula again for those tangent plane parallelograms. The idea for the area of the tangent parallelogram, again, we're using linear algebra, and we're going to use this amazing fact that if you have a parallelogram determined by a vector u and a vector v, which unfortunately have nothing to do with our transformation, that's what we call vectors. V for vectors, V for vecchio, V for victory. Coincidence. But if you have a parallelogram determined by those sides, u and v, the area is exactly equal to the magnitude of their cross product. What? Yeah, the length of their cross product, who is the vector who's perpendicular to both, happens to be exactly equal to this area of the parallelogram determined by them. And that's what we're doing here. We just had to cook up using our vector calculus business who those vectors were for us, and they're technically in 3 dimensions, so the third coordinate is 0. When I do this, I'm just going to pop it in there, just like some unnamed book did too. This is, first of all, look at my other videos on cross product properties. This is a number and this is a number, and it says if you have V cross alpha W, you could write that as alpha V cross W, and everyone nods, and yeah, but I have an alpha. Those are numbers now. I can take them out. What that says is the norm of delta U. I can do it in either coordinate. It doesn't matter where that alpha is. And if I had a beta, I could still take alpha, beta out. And then those are commutative if you're in a commutative space. So properties of cross product. Delta U, delta V times RU cross RV. And then these are numbers which are positive because they're sides of a rectangle. So they come out in absolute value, but I'm not going to write absolute value because they're positive. So now this is properties of norm. This is delta U, delta V times, and now we're at RU cross RV. This is equal to, now, here's where I'm just jumping it in there, IJK, definition of cross product, not the way physicists do it, but the way there are clever mathematical version of this is a 3x3 determinant. But to do that, I have to write these as deuce eggs to view them as three-dimensional vectors, not two-dimensional. This gives me, remember what they were, this was the partial derivative with respect to x with respect to u, the partial of y with respect to u. This is the partial of x with respect to v, and the partial of y with respect to v. Computing this 3x3 determinant, that magically gives me the partial of x with respect to u, the partial of y with respect to v, the partial of, I almost forgot it again. What did I forget? Delta u, delta v, my numbers. And then this would be the partial of y with respect to v, x, and then the partial of y with respect to v times our vector k. What does that give us? Let's move that up and show us, basically, we now have, we're going to call this guy the two-dimensional Jacobian, or when we do double integrals, this is going to be the 2x2 determinant, which is going to be called Jacobian. We'll have a similar one when we actually have vectors in 3 coordinates. We'll actually have them all in there. We'll have a whole bunch of partial derivatives, and we'll put them all in the rows and take the determinant of that, and that's the Jacobian. For now, this is called the Jacobian, and it's going to help us do change of variables for double integrals. All right, so before we give this final change of variables for double integrals, we have a definition now. This calculation or this object that came up in this derivation is called the Jacobian, and it will be true for if you go further in multivariable calculus and those types of things, or differential equations, Jacobian comes up quite a bit. What we're doing right here is, this is our definition. It's this now that we derived it from where we were doing, we temporarily cheated and said we were in 3 dimensions, but now that we get this derivation, we ignore that was in the k direction or in the z direction, and we're going to define this Jacobian to be the determinant of the partial derivatives, the 2x2 determinant of the partial derivatives, so AD minus BC, same we do in linear algebra. Therefore, the moral of the story is, you can start paying attention now, I guess. The area of the image that we were doing is approximately equal to not just du dv, but the Jacobian times du dv. Now let's show how this finally pieces together what we call change of variables in double integrals. Once we clean all this up and put it all together now, what are we using? Again, we're using tangent planes was the clever idea, and then we used areas of parallelograms on the tangent plane, and that was awfully linear algebra, which I like. And we derived cleverly this Jacobian business, and what that says is, we're going to, if we want to look at this double integral of f of xy over a general region R, what we're then going to do is, that's actually in our Riemann sums derivation, if we take the limits of m and n go to infinity, that's actually equal to this horrible symbol. But it's approximately equal to this by Riemann sums. And then what we're going to say is that dA, how did that delta A change? We just saw that's approximately equal to, this guy. So we put that in there, and then all we've done from here to here is xi is g of ui vj, and yj is h of ui vj. And then this delta A we just derived using tangent planes, again, is cleverly equal to the Jacobian times delta u delta v. And if you want here, what that technically is delta x delta y, because that's dA. But now what that's saying is it's going to change, not just switch to uv, it's going to be Jacobian times uv. Wrapping that up, the double integral over Cartesian region dy dx is going to equal the double integral over S, where S is the associated region in the uv plane associated to the region in the xy plane. And remember that we're always going to get that it's going to be r dr d theta when we do polar, for instance, but it's going to be the substitution. And then in the one-dimensional one, it was just dg du du. And this time it's now the generalized, that's the one-dimensional Jacobian. Now it's the Jacobian times the new differential. Let's do a couple examples of that. All right, example 1. We're going to start off showing you that this is exactly, it is true. You don't have to believe me. We're just going to show you that this is for polar, and we want to do the change of variables to polar form. This is actually how we do this. Is Jacobian was this the whole time. So the question says use Jacobians to derive the formula for double integrals in polar form. What we have to do is, first of all, when we did polar originally, polar started getting used because we start saying, okay, if you have a nice circle and x squared plus y squared, it's like that hits a nerve because that's r squared. So you should, once you have an object that looks like that in the r theta region, is what we were saying without telling you. If it looks like a circle, you should do this clever polar transformation or change of variables, because then you'll get a polar rectangle. And then, but if you already start with a circle, that's a polar rectangle, so it will become a polar rectangle in the transformation in the xy plane. And we're going to start off in the r theta. And that's what we did in the previous sections of this chapter when we did polar coordinates for double integrals. But we only made the move cleverly to polar coordinates when we had a region in the r theta plane which wasn't a rectangle. It was already a polar rectangle, so when we do that, you didn't notice that it was changing the shape of the object, because we already started with a polar rectangle, so we will map polar rectangles with polar rectangles. Why am I pointing this out? Because now what we're going to have is our substitution, first of all, is x is r cos theta from that right triangle. X is, so, and then this is our radius r always. And then y is r sine theta from this triangle that we always have. That's where we're getting that from, which is clever. Now that we have, and we've noticed that in this transformation, a regular rectangle goes to a polar rectangle in the xy coordinates, we're going to show that the double integral formula for polar form is going to have r dr d theta, and we're going to do that using the Jacobian instead of deriving what we did in the earlier chapter. The Jacobian xy u are r theta. In general it's uv, but now we have specifically r theta. This is equal to, now this is our functions of r theta, so that's going to be the determinant of the derivative of x with respect to r and the derivative of y with respect to r, and this will be the derivative of x with respect to theta and the derivative of y with respect to theta. But now we have those functions specifically. So doing that, I get, this is equal to the 2 by 2 determinant. The partial of x with respect to r is cos theta. The partial of y with respect to r is sine theta. And then now the partial of x with respect to theta is negative r sine theta. And the partial of y with respect to theta is r cos theta. And now AD minus BC, I'm computing a determinant. This is going to give me r cos squared theta minus plus r sine squared theta, which is r cos squared theta plus sine squared theta. This is 1, which is r. So the Jacobian is r in this case. Therefore, what that says is a double integral over a general rectangle r of f of x y dy dx is going to equal the double integral over this region S is going to be f of r cos theta, r sine theta, r dr d theta. And this is the Jacobian. Let's do another one. For our second example, we're going to evaluate the double integral e to the x plus y over x minus y dA. If we keep that Cartesian, I don't know how to integrate that. That's the problem. Same with substitution rule. I don't know how to integrate x e to the x squared, but if I make a clever substitution, I know how to get myself out of that. And I can integrate with respect to my new variables, u. In this case, I've got u and v we're going to use. In the worst case scenario also, they're not going to give you the transformation, but hopefully in most of the scenarios, especially in an exam, I'll give you it. But what we're seeing is I don't know how to integrate that, so I want to change it to two simpler things and get rid of the plus and the minus. So I'm just going to let u equal x plus v and y equal x minus v, and then that's going to give me e to the u over v. And then if one of them is constant, I can just hold v constant, take the derivative, and then we're in business and I can anti-differentiate, and that's going to be the idea of what I'm seeing. But to do that, we have to do several steps now. First step we have to do is, this is the transformation. This shouldn't be here. It gave us in the problem, it says R is the trapezoidal region with vertices this guy, this guy, this guy, and this guy. So they gave us this guy, the Cartesian one. I want to change to some other unknown transformation, and I don't even know what it is. I had to make it up. Once I've done that, I need to see how this transforms into, so he's not there yet. That's what's going to magically appear in my next step. Why am I doing that? First of all, I want to make this change of variables so I can integrate this. It'll just be u over v, which I could probably deal with in the integration. But then the dA I have to deal with, and I'm going to do that with a Jacobian. But the other step that you have to do is, if my bounds were this to this, when I do the change, I need to see what my new bounds are going to be for this region when I integrate with respect to u and v instead of x and y. So we don't have this picture magically, and we're going to quickly derive it right now so that we can see that this transformed to this under the transformation. This is t, our transformation that maps u to v into the x and y images. Let's see how that transforms. Trying to draw this region S, pretend it's not there. What's going to happen is I'm just going to show how to get this one from this line segment and see how this guy actually transforms into that segment. What we're doing is, we've been given this horrible integral. We want to make a substitution. They didn't even give us what it is. If they're nice, they give it to us, and then we can reverse this argument slightly. But in the worst case scenario, I have to make a substitution. So I'm going to call u this and v this. But this is not the transformation t that we just derived. That's t inverse. It's telling where x goes. X goes from here to here. X and y. Therefore, we must find to find the region S, we have to find the images of the boundaries of these lines, essentially, under this transformation T inverse. And then that will give us these lines in the UV plane. For instance, if I look at line L1, this guy, that's the equation y is 0 and x can be itself. And in particular, what that's going to do is say that u is x and v is x, i.e. they're equal to each other. So in the Cartesian plane, they're the line u equals v or y equals x you're used to. Or this function gamma is this curve in the UV plane, so we're going to get that line now. If we keep going and trace out all these other curves, the arrows are indicating this one first, then this one. The double arrow will now map into this one. This line segment, whoever he is, x plus 1 is 2. And then if I do this line segment, it will map into this line segment. Notice that their orientation is reversed. And then if I do this last segment, I will get that segment. So I get a trapezoid maps to a trapezoid, but just in a different orientation. Why have I done that? Because I can now find my bounds. My bounds are, where does u go from? -2 to 2. And then we can go from, v is going from 1 to 2. We'll figure out our bounds in a second. Let me redraw that. But this is the first step. If we have to make our own transformation, we're given the inverse actually, and then if we're given R, we have to find the bounds of S also. And this is why we did this business. Now let's use that to compute the double integral. All right, now that we have this, you can ignore how we generated it. Now we have a region S. The point of that was we need to know the bounds on S. We need to know what our transformation is. Also, remember that we just had u was x plus y and v was x minus y, and therefore that says x is 1/2 u plus v and y is 1/2 u minus v. We're going to need those for the Jacobian also we have to compute. Now we have the bounds, so we can compute our double integral. What we need is the Jacobian dxy duv. And for that, we did need, this is t inverse and this is t. So we do need this one. Now we're going to take, this is going to be the 2×2 determinant, the partial of x with respect to u, the partial of y with respect to u, the partial of x with respect to v, the partial of y with respect to v. Doing that, we're going to get, this is equal to, specifically I could take the partial derivatives now. What am I going to get? The partial derivative of x with respect to u is 1/2. Partial derivative with respect to v or y with respect to u is 1/2 also. The partial of x with respect to v is 1/2, and the partial with respect to y with respect to v is negative 1/2. And so this 2 by 2 determinant becomes negative 1/2 times 1/2 minus 1/2 times 1/2, which is negative 1/4 minus 1/4, which is negative 1/2. We actually have to, it's extremely bad notation, but we have to take the absolute value of the Jacobian, is technically what the theorem says. I forgot it in there, but when you get this, you can ignore it's going the wrong direction. Take it's the magnitude of this. So we have to take the absolute value, so we get 1/2. I'll write that when we write the general formula. Now we have all the pieces that we needed. You have to define what your transformation is, but then that's T inverse when I want to make my substitution. Then I need to find T so I can find the Jacobian. I use T inverse to find my new region S for the bounds. Using T inverse, we found the bounds on S now were 1 is less than or equal to V is less than or equal to 2, and U is between negative V and V. So it was easier to phrase it as a type 2 region in the UV plane, not a type 1 region. And then we used T to compute the Jacobian, which ended up being the absolute value of the Jacobian was 1/2. Now let's use that to change the variables in a double integral. All right, finally integrating this, what that now says is getting all the pieces together. I use the inverse transformation. I define a transformation x, or u is x plus y, and v is x minus y. That's T inverse. I use T inverse to find S and the bounds of S. Then I have to find T so that I can find the partials and the Jacobian of the x's with respect to the u's and v's. Once I now have that, I saw that my Jacobian, the absolute value of our Jacobian this time of x, y, u, v, we found was 1/2. Therefore, this is equal to, now we have our bounds. This is saying this is the integral from 1 to 2, the integral from negative v to v of e to the uv, absolute value of negative 1/2 times du dv. Now, this is simply a constant we can take out. This is 1 to 2, negative v to v of e to the u over v du dv. Now we're holding v constant and integrating with respect to u. So what's the antiderivative of e to the ax? 1 over a e to the ax. My a is 1 over v, so that's going to be 1 over 1 over. That gives me 1/2 the integral from 1 to 2 of v times e to the u over v, evaluated from negative v to v dv. Now what do we put that? We put v where u is, and what are we going to get? We're going to get 1/2 the integral from 1 to 2 of v times e to the 1 minus 1 over e, it looks like, when I put the v's into here, dv. So moving that up and moving the constants out, you can see that this was a much easier integral than trying to integrate. I don't even know how to do that, but this was the idea. It's a much more difficult process. Wait till you see it for triple integrals. Even more fun. What we now have is just the antiderivative of v, which is going to be e squared minus 1 over 2e, that constant, times 1/2 v squared evaluated from 1 to 2. This is going to be e squared minus 1 over 4e evaluated from 2 squared minus 1 squared, which is going to be 3e squared minus 1 over 4e, a number. Again, to recap quickly, you're given some horrible integral and they don't even give you a transformation. What you have to do first is define a transformation in terms of u and v, which is actually T inverse. From T inverse first, I find the region S in my UV plane, so then I have my UV bounds. And then I have to find T, the actual transformation. I use that to find the Jacobian. Once I have the Jacobian, I can now do the change of variables from the xy to the UV coordinates and compute the double integral using the change variables. Please subscribe right here and hit the notification below. You'll get notifications for this series and a bunch of other ones on our channel.